In this section, I'd like to think about the difficulties we have with mental arithmetic. Because the interesting thing about mental arithmetic is that we're not all that good at it. It takes us about 5 years to become fairly fluent in our native language. But quite often in our education system, it takes another 5 years to learn mental arithmetic. And even as adults, we make lots of mistakes, more significant mistakes in a behavioral sense than we make in our speech. Perhaps a key factor in the limitations to our arithmetic capabilities is how our brains understand numbers. The issue is learning the meaning of numbers. So what's the process for learning the meaning of a number like 3? Let's suppose that we see a group of objects and the inputs are processed through this usual sequence of visual areas. For example, if we're looking at a group of 3 birds, there's going to be a cascade of receptive field detections running through the areas. And perhaps at some level of receptive field complexity, there are fields that are detected relatively frequently in response to the presence of 3 objects. So if this illustrates that particular visual area, and this illustrates the auditory area that's able to discriminate between words, then once again, if we see a group of 3 birds, visual columns will detect their receptive fields, and if at the same time we hear the word 3, when at the same time as we're seeing the 3 objects, auditory columns will detect their receptive fields. If we looked at a number of different groups of 3 objects, and each time we also heard the word, but with lots of variation in the objects forming the group, then in one visual area, there'd be a set of columns that are often detected their receptive fields at the same time as a set of columns in the auditory area. Then by the usual semantic memory mechanism, those visual columns could acquire recommendation strengths in favor of saying 3. However, this assumes that some area has receptive fields on a level of complexity that can learn to discriminate between the presence of 3 objects and the presence of any other number of objects. This seems to exist for humans and for the number 3 and for groups of other small numbers. We can almost instantly say there's 2 items in the group in the top left, just as fast for a group of 3 or 4. But most of us begin to slow down with a group of 5 or 6, and with 7, 8 or 9 we're basically reduced to counting. Although we can immediately see that the group at the bottom right is bigger than any of the others. But when we get to even larger groups, like these 2, it's not always possible to tell at a glance which has the larger number of objects. So we can identify the size of groups at a glance without counting for groups of 4 or less, but it gets steadily more difficult beyond that. And interestingly, experiments show that animals can distinguish between groups of 1, 2 and 3, occasionally 4, but never beyond. But in contrast, note that we can identify a simple object like the oval, or a complex object like the face of Einstein, and the complex object doesn't take an obviously longer time, unlike numbering larger groups of objects, and like determining the example of 2 objects on the left but 47 on the right, even if in both cases the sub-objects are well organized. So that suggests that the problem with arithmetic is that we don't have a cortical area defining receptive fields in a range and complexity that's able to discriminate between different numbers, and we share that limitation with animals. Evidently there's not been any sufficiently strong natural selection pressure in favor of such an area. So we have to find a way to work around arithmetic problems, memorizing verbal associations like 9 12s or 108, rather than developing pseudo-visual relationships between numbers. And of course an implication could be that more cortical areas might be added to take human intelligence or machine intelligence beyond current human levels.